So the proposal we had submitted, we called it DeepBET, is about using some deep learning methodologies in order to help us collect appropriate data for reverse engineering the behavioral targeting mechanisms of ad networks. So the idea was that we need to collect data, that is, user profiles, to query ad networks with, that comprise as a large subspace of the possible user profile space as possible. So in order for us to do that, we propose a methodology which basically comprises 3 steps. The first step is based on selecting some websites that will be used to create the user profiles. So we basically were based on the top 100 websites from various AdWords Ads Planner categories. So based on that, we use some deep learning methodologies, a deep optimal machine basically, in order to create to extract some high-level representations of these websites. And based on that, on these high-level representations, go ahead and cluster the websites into a tree of clusters and subclusters. This is a method we have used to do that, which is called the Bayesian roster. It's a non-parametric Bayesian method that infers both how many clusters you have, what the subclusters are of each cluster, that is all the hierarchy, and of course, which websites are members of each cluster. Now, based on that outcome, we select few representative clusters. Basically, we select some clusters, and only the representatives of these clusters, which are inferred from the Bayesian roster tree, are used to create, to construct the user profiles. Now, after that, we need to create sequences of websites that hypothetical users have visited. And we want to do that in a way that is as diverse as possible, so that we can have profiles that represent different combinations of user interests. So in order to do that, we first create random sequences of the selected websites, and then we use again a deep learning method, which is called the long short-term memory autoencoder, which basically creates some vector representations, which are abstract representations of these sequences, the randomly sampled sequences. We then cluster these sequences, again using a Bayesian row tree model, and based on that, we select some representative sequences, which are basically going to be used as the user profiles, in order to query the ad networks using these basically profiles that we have selected this way. So once we have this, followed this procedure, we basically end up with a number of sequences which constitute very diverse patterns of sequences of websites that a user may be visiting. And this constitutes a very large subspace of the possible user patterns, behavioral pattern space. Now, since we have selected these websites, we can go ahead and query the ad networks with these profiles, this sequence of websites. And then, in order to perform inference for what the ad networks, how the ad networks use this information in order to target the users and infer, for example, the correlations between interest type combinations and ad network outputs, how long temporal dynamics the ad network postulates, and so on. We use a method which is called dynamic Bayesian probabilistic matrix factorization. It's an algorithm we have developed in our lab, and it is published in some major venues. And we have tried this. We have already started to test it, and we have obtained very promising results, both on the side of sampling the artificial user profiles and on the side of how robust the inferences are, the obtained inferences are that are obtained from the DeepBET algorithm. So that's the point, mainly. And if you have any questions during the poster session, I'll be there to answer them. Thank you.
Thank you. Thanks for opening the much faster session. Okay, so this is all right. The next talk will be given by Marc, who is coming from Northwestern.
Good afternoon, everyone. I'm Marc Anthony Warrior. I'm a grad student under the guidance of Dr. Alessandro at Northwestern University. I'll be presenting to you today our system, Alibi, where we try to turn user tracking into a user benefit. So before I go any further, I'll be talking a lot about identity, so I'll just give a quick definition of what identity is in the context of our system, Alibi. So identity is a set of attributes. It could be your height, your hair color, the kind of food you like. But the important thing to remember is that your identity is not necessarily global. For example, my boss probably sees me differently than my family sees me. They probably see me differently than my friends see me. So we try to control the attributes that form our identities for different groups. So now that we've given this definition, we have the power to answer the question that everyone on the internet is asking, who are you? So with the definition of identity that I just gave, there's a lot of different ways to answer this question. For example, to Netflix, my identity may be, I like comedy movies and action films. But to Amazon, my identity might be, I like to buy video games and pop music. So there's a lot of different ways to answer the question of identity because each site is dealing with a different set of attributes. So for our system, we kind of divided the internet into two groups. Particularly, we look at trackers, and then there's everyone else. So the interesting thing to note about trackers is that the identities are happening for us. They're taking the question of who are you and answering it themselves by taking matters into their own hands. They're tracking the way that you use their site. For example, Amazon doesn't have to ask me what kind of a shopper I am. They know exactly what kind of shopper I am because they're tracking the way that I use their site and keeping a history of that. So they already know my shopping interests. It's effortless on my part. I don't have to go out of my way to tell them. But meanwhile, while trackers have identities for us, such as the examples that I've listed there, everyone else that isn't forming identities, instead of having identities, they have problems. If we don't have identities, we may have Sybil attacks, where you have one user pretend to be a number of users in order to take advantage of the system. If you don't have identities, you may have impersonation, where one user pretends to be another user. If you don't have identities, you may have synthetic accounts, where a robot pretends to be a real user. So in light of those three issues, you may have some situations where there's a website or a service that isn't particularly interested in forming an identity for you, but they're so afraid of those first three issues that now they have a lot of authentication schemes. They say, okay, you have to have a complicated password. You have to give us your email address, give us your mother's maiden name in case you forget your password. So re-authentication on sites and services that may not even be concerned about your identity now becomes more complex than it has to be. So we have this kind of a contradiction where on one hand there's groups that are forming identities, often against our will, and then we have another group where we need some basic identity, but they don't have any, and it becomes really inconvenient. So we ask ourselves, is it possible to take the work that the trackers are doing, that's part of the internet, is difficult to avoid, and use it to solve issues on the sites that have these problems where there's a lack of identity? So to do this, part of what we need to do is get back the information of, well, what are these identities that the trackers are building for us? So the more straightforward way for us to do that is we do get a reflection of the identities that are being collected, and that's in the recommendations we get back. If on Amazon, if I'm obsessed with shopping for flat screen televisions, then the recommendations I'll get back will be flat screen televisions. That's a reflection of the identity that Amazon has for me. So that leads us to the development of the system that my lab has in mind, which is Alibi. So for us, the recommendations are the attributes. And we build a anonymous identity for our system using the recommended items. We reduce the size of that space by looking specifically at the categories. For example, in the previous slide where I showed TVs, we may not necessarily be concerned with, this is a particular model of television, but are you being recommended televisions? And then once we have a profile built on the set of items that you're being recommended, we're able to distinguish you from other users without asking for personal information. And the more sites that we do that across, the more distinct that you become. But the important thing is that the users are submitting the sets of recommendations at the beginning of the system. So the users have absolute control over the attributes that are going to form their identities within the Alibi system. So why use Alibi? So the end goal is to, of course, tame civil attacks. We don't want people to be able to pretend to be someone they're not. We want to be able to recognize returning users without them having to do anything extra. We want to take the effort out of identity. You shouldn't have to jump through hoops to identify yourself on a site that isn't actually concerned about who you are. And we want to make sure that we're preserving privacy. If you have to identify yourself, you shouldn't have to use personal information, and that's what Alibaba offers. If you have any more questions, you can ask me.
Thank you. PowerPoint? Yes. Okay. Christo is going to give the next talk from Northeastern.
Thank you, Augustin. So my name is Christo Wilson. I'm a professor at Northeastern University, and I'd like to tell you about our new work studying Uber's surge pricing algorithm. So for those of you who've never used Uber, so Uber is a ride-sharing service that has become extremely popular all over the world. So it's just an app. You open it up on your phone, you tell Uber where you are, and then you click a button. And then a few minutes later, a car shows up and picks you up and takes you wherever you want to go. So it's, again, extremely popular now. It's much more convenient than going out and trying to hail a cab. So it's expanded all over the world. They have millions of customers, hundreds of thousands of drivers. However, Uber is also quite controversial for many reasons, but one of the big ones is surge pricing. So during times of extremely high demand, Uber uses a dynamic algorithm to change the prices. So in this case, Uber is telling the customer that the surge multiplier is 2, meaning they're going to have to pay double the amount if they want this ride right now. So the strange thing about this system is that it's totally non-transparent. Right? You have no idea what the supply is or what the demand is or why you're being quoted this price. Right? You just have to trust Uber that this is fair. This is different than other marketplaces that we're sort of accustomed to. Right? This is different than Airbnb or eBay, where you can see all of the products that are available, all the prices, all the inventory, and that gives you the power to make informed decisions. Right? Uber does not work this way. It is a black box. So this has made the service quite controversial. However, the business model is now widely emulated. Right? There's Uber for everything, from dog walking to food preparation to whatever you want. So the question for our study is, given that this kind of black box dynamic pricing system is now so popular, right, we really want to understand, how does Uber actually work? So the goals of our study are the following. First, we want to understand, how is surge pricing actually implemented? Right? How does the system work? Once we figure out how it works, then we can start looking at workarounds. Right? So maybe there's an approach that people can use to try and save money and avoid surge pricing. And then third, and perhaps most importantly, we want to understand the impact of surge on passengers and customers. Right? Maybe the algorithm is behaving as intended and it's having sort of beneficial effects on drivers and customers. Or maybe it's not. Maybe the incentive mechanisms are wrong and it's actually having a detrimental effect. So to understand how Uber works, we use their own smartphone application. So we ran 43 copies of the Uber app for 2 months, and we collected a ton of data from New York and San Francisco. So from the app, you can get a lot of very useful data. So you can get the wait times for cars. You can actually observe the available supply and the fulfilled demand. So you can see all the cars that are available and sort of driving around. And when those cars disappear, it means the car got booked. So we can estimate the demand. And then finally, of course, you can get the surge multipliers. So over time, we can see how are surges changing as supply and demand change. So our study just came out recently at IMC, just a few weeks ago actually. And given this is a 5-minute talk, I don't have time to tell you about the results. Too bad. If you want to talk about the results, I'm happy to tell you at the poster. Instead, I'd like to talk about the impact. So the first thing that happened when we published the study is that the press went crazy. So this is actually fantastic, right? If the goal of this is to make data and algorithms transparent, you really need to make the public aware of what is going on. So outreach to the public, outreach to the press is really, really important if things like the DTL are to succeed, right? We have to enfranchise users, and working with the press is a big part of that. Second, I want to tell you about the bug. So this graph is showing how frequently Uber changes surge prices over time. And the key feature is actually this sort of stair-step pattern. So in February 2015, Uber updated their surge prices about every 5 minutes, right? That's why it sort of plateaus every 5, 10, 15 minutes. And this was very consistent. However, in April of 2015, the behavior changed dramatically. The practical impact of this is that we saw users essentially getting random surge multipliers at random times, and we couldn't figure out why. So we talked to Uber, and it turns out that this was a consistency bug in their system that was giving people incorrect prices. This was going on for 6 months until we told them and they finally fixed it. So again, high impact. Finally, on the day that our paper was published, Uber announced a new transparency blog, which is great, right? We want to promote transparency. This is having the intended effect. In fact, the title of their blog is almost exactly the same as the title of our paper, which is great. So if you'd like to know more about how Uber's surge pricing algorithm works, I'll be happy to talk to you during the break.
Thank you. Now you can attack them for plagiarism. Okay. Okay, the next talk is going to be given by Maxime Gabrielkov.
Okay, hello everyone. My name is Maxime Gabrielkov. I'm from Columbia University, and today I will be talking about zero-knowledge transparency and safe audit tools for end users. And let me first talk about why we do this research. Currently, we have web services that are working mainly as black boxes. They take a set of user inputs, for example, watched videos, products you bought, your emails, or search key terms, and give you targeted outputs, like ads or recommendations. The problem here is that there is no transparency, and there have been some evidence of data misuse. Some companies are targeting you ads based on your really private data. To address this issue of web services being opaque, transparency tools were developed. Transparency is great, but there is even more privacy concerns here, because currently for transparency tool to work, you need to give them access to all your data. That means you need to give your Gmail password if you want to know how Google targets ads to you. Of course, you can say that we can develop a transparency tool that are privacy preserving, but can we solve this issue once for all the tools instead of developing an ad hoc feature? And the solution here is to use a trusted third party, for example, a data bank. And that's the approach we are taking in this study. Now I will talk about how we got our preliminary results. X-Ray is a transparency tool that was presented at Unix Security in 2014. It was developed in our lab, and it's looking at the inputs and outputs the user sent to a web service, and then shows the users why certain targeted outputs were shown. For example, which email triggered a certain ad. We are using a dataset on Gmail from X-Ray. As a trusted third party, we are using AirCloak that was also discussed here before. It's a data bank that is allowing anonymous analytics. Its security is ensured by hardware. Basically, once users securely push their data to AirCloak, no one can retrieve it back in a clear way. Only anonymized analytics are available. So basically, we took a dataset of X-Ray on Gmail and we put in AirCloak. And then we run the same infringement of targeting that was done in Gmail, in X-Ray, sorry. And that's what we found. This figure compares transparency tools versus zero-knowledge transparency tools. On the x-axis, we have the statistical confidence in raw data of X-Ray. And on y-axis, we have the statistical confidence from the same data that was put in AirCloak and run through AirCloak. You can see here the confidence level, the less is better. You can see that using AirCloak increases the statistical confidence, but by a fair amount. Just to give you an example, here we show the number of ads that were identified as targeted. In blue, we have the raw data of X-Ray. It's all the same in 3 figures. And in red, we have the same data from AirCloak. And here we want to show that by varying the threshold on the confidence level P, we can achieve different results. For example, on the left, we can be less selective, and we can identify almost all ads as it was in raw data, but we'll have a huge amount of false positives. Whereas on the right, we can be really precise and really picky, we can identify only 12% of ads, but there will be no false positives. And currently, we are working on making these things more precise to achieve the higher recall and precision. Sorry. So if you're having particular scenarios that you're planning to use with real sensitive data, or you don't find any tools that can be used for that, please come to our poster and talk to us. We will be really happy to discuss that. And thank you for your attention.
Given by Alessandro. Alessandro will be presenting the next poster.
Thanks. I'm from Trinity College, Dublin. I want to present this project about how to give the user the ability to detect evidence of profiling by a search engine. And when I talk about profiling, I mean, imagine it has to be independent from a previous tracking or anonymous or logged in connection. So imagine just you go to an internet cafe, you sit and start a search session. And during this search session, the search engine will learn something about us. Can we understand what they're learning, especially if it's about sensitive categories, like sexual interests or health issues? And we want to provide a tool for the user that can be used directly on the browser. So let's just look at how the search engine works. The blue part is the search results, and usually they don't change a lot because the search engine wants to guarantee a sort of rank stability. But the red part, the adverts, they change. And since Google or the search engines are an adverts company, they want to use all the information they have about us to maximize efficiency of the ads. So we could use the adverts, analyze the adverts to try to understand what they know about us. Like, does Google know that I'm a gambling addict or not from my previous navigation session? And of course, it's not so easy because probably these ads are just because the query is about gambling addiction, right? So it's very hard to decouple what Google knows and what is just serving because of the query. So our idea is to regard the search engine as a black box, where the inputs are the search queries and the clicks of the user. And the output are the search results and the adverts. And we want to infer the hidden profiling of the search engine, that especially the one that can be related to sensitive topics. And the idea is to use a typical black box approach. So we have to find some probe queries to send in the background that are kind of unintrusive to assess the search engine learning potential and to try to understand what they know about us. This probe queries has to be plausible in a way that the search engine doesn't think that the topic is changing, and ambiguous enough to force the search engine to reveal what it's thinking about us. Let me just show an example. So this is a typical example of a probe query that would be run by the plugin in the background. So what it does, it just, for example, can be regarding health issues in general. If I use this very generic query, Google in the beginning of the navigation, as you can see, doesn't serve any adverts. Then after I start to navigate, and for example, I search about diabetes, and I go on, and like my normal navigation, I click, and the search engine is learning about me. And again, when I will use again the probe query, now the adverts are related to my previous session. So in this way, I can decouple the query from what actually Google is hidden learning. And this works for Bing and for Google, and we can get very accurate results, and we can find evidence of privacy disclosure with very high accuracy. And the interesting thing is that the search engine appears to learn very quickly, like in 5 queries, and to have a very short memory span. So maybe to avoid the creepiness effect. So it just, it's not enough to be anonymous. It's not enough to just log out, because during the search session, they will learn about it. And the thing that affects a lot learning is the clicks, is the feedback of the user. So we have to keep that in mind if we want to kind of hide or contrast. The most sensitive thing is actually clicking on the ads or clicking on a link to let Google know that we are actually interested in that specific category. So if you have some questions, just come to see the poster. Thanks.
Thank you. Okay, the next talk will be given by Yinzhi about how to make the web forget about us.
Yeah, thanks for introduction. So my name is Yinzhi. I'm from Lehigh University. Today, I'm going to present towards making system forget with machine unlearning. So first we'll talk about why do we want machine to unlearn stuff. So let's assume that we have a machine learning model, and what machine learning model does is to find what email is a spam or is a ham, which is a benign email. So this is how it works. So we have a benign person. He labeled like spam as spam and benign as benign, and then generated training data. And the training data is going to generate a model, and the model going to classify spam as spam. However, this is not always the case. Say, for example, now we have an attacker, and what the attacker does is always label spam as benign email and benign email as spam. And in this cases, this model will be polluted. We call it a polluted machine learning model, and therefore, when we have a spam, it may probably be identified as benign email. And in these cases, we may want the system to forget what they've learned before. So this is the first reason we want the system to forget. There's more reasons. You can look at my poster. So now let's take a look at how do we make system to forget. So now we need to introduce a new type of system called static query learning. This is how it works. Say we have different training data, x1, x2, x3, and x4. And then in this cases, instead of generating the learning model, we generate a new layer called summations. And this summation does is a transformation of original data and then add them together. We can have different summations, like summation 1 and summation 2. And then what we're going to do is we generate the learning model purely on the summations instead of the training data. And now let's come to unlearn. So unlearn becomes easy because we can just remove the training data, which is, for example, x4. We remove it from training data. And then we need to update the summations. So what we do is we subtract the transformation of training data from the summations. So we update the first summation, the second summation, and then we recompute the machine learning model. Now our unlearning works. It's both complete because you can see the result is exactly the same as the data never existed before. And second, we are fast because the number of summation is much less than the number of training data. So that's why we are fast. So we answer the first question. So that is, how do we unlearn? The second question is, so what do we unlearn? You know, we have data, is data being injected by attacker, and how do we find out which data to unlearn? And this comes to active unlearning. So think about it. So how do we find out a learning model is polluted or not? So that is, that we look at the accuracy of the model. If accuracy is low, then it's polluted. So these cases, say we unlearn some data, and then if that machine learning accuracy increase, and probably this data means it's polluted. On the contrary, if after unlearning, the accuracy decrease, that means that this data probably is unpolluted. That means we can use our machine unlearning as presented as an indicator of whether a data is polluted or unpolluted. So this seems easy, but the problem is there's so many possibilities of data. It's an exponential number of combination of data. How do we deal with that? So now let's come to the intuition. So how do we solve the problem? So here, let's take a look at a graph. So the x-axis is the class size, which is the class that we're going to unlearn, and the y-axis is accuracy. See, it starts increase. Probably as we mentioned, it is a polluted data, and then it keeps increasing until it reaches a peak. So that means that, okay, until the peak, we started to include more unpolluted data. So that means if we come to the peak, that is the ideal size we want to unlearn. But this is not the end. We want to find out, okay, how do we find the peak? So how we do that is we first use a coarse-grained search. We find different intervals, and then we find the correct intervals, and then we start a more fine-grained search until we find the peak. So this is the intuition of our active machine learning. So thank you guys. I have a little bit joke here. So I'm sure you'll forget what I'm talking about because we make you do so.
Okay. Okay, the next talk is given by Francesca, and this will be the last talk before we can actually interact with all the speakers of the cluster. Okay.
Hello, everybody. I'm going to introduce our proposal. So our proposal was based on two general ideas. The first one is the privacy by design, which is a paradigm that consents to obtain a privacy and to inscribe privacy in an analytical process by defining some properties of, for example, of data and some assumption about the attackers. The second idea is the risk assessment. So in our case, the privacy risk assessment that aims to classify users, a set of users, based on their risk. For example, their risk to be re-identified. So the idea is to combine these two aspects in a framework, in a general framework, in which we have two actors, a data provider, which collects a huge set of data by some users, and a data analyst that can ask data to the data provider to provide some external services. So the data provider defines which are the dimensions of the data, makes the query, and analyze the privacy risk of all its users. Only if the privacy risk is compliant with its expectation, these data are delivered to the data analyst. Otherwise, there is another module that operates a sort of mitigation on the data and try to make safer the users that are some problem. This process is iterated until the data provider is satisfied. What do you want to provide is the empirical privacy risk, so the real risk of this set of users. And we want to define a ROC curve, so we want to give a coverage measure of this risk, and a number which represents the area under the curve. With this information, we want to provide this catalog that can help the data provider to decide if the data are safe or not. So we have all the dimension of the data and all the background knowledge, and we have on the z-axis the representation of the risk with this particular set of dimensions. So for this aim, we want to provide some model for the quantification of the privacy and also the data quality of the released data, and to define a set of specific knowledge of the attacker because of the restriction on the privacy by design. And we want to evaluate this model with some experimentation with real data. So that's it. I have the poster in the corner if you have a question. Thank you.
Thank you.